The first thing that you might notice about this system of linear equations is all of these zeros in the constant column. When you see those zeros, you have what we call a homogeneous system. One solution that might occur to you is having everything equal to 0. That will work for any homogeneous system. It's not what you would call an interesting solution. We would call that a trivial solution. Which brings the question, are there any non-trivial solutions? Let's find out. We'll jump straight to the reduced row echelon matrix associated with this system. And for reference, let me label the columns according to their variables. Here we have a leading one, here we have a leading one, and here we have a leading one. X sub 3 is a non-leading variable. We can live with that. We'll assign x sub 3 a parameter. We'll call it t. That's our solution for x sub 3. Now let's rewrite the information in terms of the variables. Our first row is x sub 1 plus t equals 0. The next row is x sub 2 minus t equals 0. And our final row is x sub 4, just fine and dandy, equals 0. Now let's rearrange the information in terms of a solution. This first one gives us x sub 1 equals negative t. This second one gives us x sub 2 equals t. And we just carry over this final one, x sub 4 equals 0. So yeah, we've got non-trivial solutions. The existence of a parameter guarantees non-trivial solutions, an infinite number of them. And what guarantees the existence of a parameter? Well, we've got 4 unknowns and 3 equations. More unknowns than equations guarantees us non-trivial solutions. Let's go back to our original system and look at each of the columns as matrices. This combination of column matrices we can modify. Let's make them into coefficient matrices. And because we've taken out the variables, we'll place the variables in front. And now we're just adding them all because we've got the signs inside as part of the coefficients. Now remember our solution in terms of parameters. Let's write it like this. If x is all of these, we can write x. And to indicate that this x refers to a column matrix, I'll designate it with a little arrow on its head, or maybe it's a feather. Okay. And remember that the solution that we had found was negative t, 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 and 0. That's a general solution, which we could write as that column matrix multiplied by t. You see what I've done here is I've slipped in this notion of multiplying these column matrices by some number. And if t equals 1, we can just eliminate that t. And that would be a particular example. Let's try this. Let's let x sub 1 be negative 1. So let's just make this negative, and we'll eliminate the x sub 1. X sub 2 is 1, so we'll just keep this the way it is. X sub 3 is 1, we keep that the way it is. And x sub 4 is 0. So we're going to multiply this whole mess by 0. We're going to eliminate this final matrix. So let's take a really close look now at what we've ended up with here. We're summing up these column matrices. Minus 1 is minus 2, plus 2 is 0. Minus 2 plus 2 is 0, plus 0 is 0. And minus 3 plus 1 is negative 2, plus 2 is 0. And we can rearrange these just like we would do with algebra. When we move this matrix over here to this side of the equation, the sign changes. It's now positive. We can eliminate this zero matrix. And now what we have is two column matrices which sum to form this third column matrix. This matrix is a linear combination of these matrices. This notion of linear combination is something which we will look at much more closely in the future.